you've already seen a little bit of Cypher already, but we're switching gears here. We're now in a Twitter model where we have tweets mentioning users. So hypothetically, here we're interested in users or tweets mentioning users, and we want to get just a simple data frame of users ranked by how often they've been mentioned by tweets, at least in this very small sample of tweets. So here we're matching on tweet-labeled nodes with outgoing mentions relationships to a user. And then we're returning the username of the user as username, the count of how many tweets as how many times they've been mentioned, and then ordering by that descending and limiting 5. So these are just our top 5 users by mention. So that's just a very basic hello world example of how you'd connect to Neo4j from R, write a Cypher query, and get your results back. And that's done with the Cypher function within our Neo4j, where the first argument is that graph object we created earlier, and then the query as a string. And then we've assigned that to a variable data, and data is now just your regular old data frame in R. And we have some usernames and a number of mentions. So that is the R Neo4j 101. And that's probably the most used function in R Neo4j is the Cypher function, where people just write a Cypher query and get the results back as a data frame. OK, let's look at some very basic visualization or charting or plotting. Who here has used ggplot? OK. I mean, it's like the most used plotting library in R, probably. So fairly popular within the R community for building really simple charts and plots. So with the data frame we just built, we can very easily create a bar chart where we have the height of the bar is the number of mentions. So we could take in a couple of lines of code, we can take information from our graph and visualize it as a bar chart. Bar charts aren't terribly exciting, but the point is that you can easily take a question from your boss and turn it into a chart in a couple lines of code and then forget about it, which is very nice. That's probably the main use of R is ad hoc reporting and analysis. So you can very easily grab your data and throw it into a bar chart. And so here we have on our x-axis our users, and then our y-axis the number of mentions. So we see that Hadley there, number 1, with the most number of mentions. So like I said, bar charts aren't terribly exciting. So let's do something a bit more fun. So let's make a heat map of hashtag co-occurrences. So of course, if 2 hashtags tag the same tweet, then we're going to say that they have co-occurred with a frequency of 1 at that point. So in Cypher and in Neo4j, it's pretty easy to get that data out. I had to do some stuff here at the beginning, so we didn't just grab all hashtags, because that would have been a very busy chart to look at. First, I'm just grabbing the top 10 hashtags simply by count. So matching hashtags, tagging tweets, getting the top 10. And then in the bottom here, I'm finding how many times they co-occur. So here I have a hashtag on the left that's tagging a tweet, and then another hashtag that's tagging the tweet. So it's finding all pairs of hashtags, or at least out of the top 10, and finding how many times they've mutually tagged a tweet, or how many times they've co-occurred, and then returning that as sort of an edge list, where we have the count as the weight, and ordering by weights descending. So if we run that query, we get something like this, where the first column, or I guess the first 2 columns, are the 2 hashtags that are co-occurring, and then the weight is how many times that they've co-occurred together. So our stats in data science have occurred together 48 times in this data set. And then we'd have some redundancy here because it found both our stats in data science, and then it found data science, our stats. But that's OK for the visualization purposes. So again, we just used the Cypher function to grab this data from the query we just wrote. And then we can very easily, within a few lines of ggplot, get this into a heat map. So here we can see that, for example, data science and big data occur pretty frequently together. And so do data science and R stats. So this is a symmetrical chart here, just a heat map of hashtag co-occurrence. And again, the point is that I was easily able to make something somewhat advanced in just a handful of lines of R code and of Cypher query. OK, let's look at graph algorithms. So there's an iGraph library that's pretty popular in both Python and the RStats world. And it, for the most part, exposes all graph algorithms that are available. So let's start looking at some of those. So the first step to using iGraph is to first pull out what I like to call a subgraph out of Neo4j. So the first thing you need to do is write a Cypher query where you're going to pull out an edge list of the specific subgraph that you're interested in analyzing further within iGraph. So here, hypothetically, I'm interested in users retweeting other users' posts. So to get that information, I need a match on users posting tweets, where that tweet retweets some tweet, and then I want to also get the user who posted that tweet. So this is just users retweeting other users in a nutshell. And then we're returning the username of the first user, the username of the second user, and then a count as weight, because iGraph will take weights into account as it's doing its algorithm. So that's an optional thing you can do, is return a weight. And then this is returning what iGraph refers to as an edge list, where you have a source and a target node. So this is a list of nodes saying this node is connected to that node. So here we've taken, our data is stored in Neo4j, as with this model, but then we can infer subgraphs out of it to analyze within iGraph. Because within Neo4j, if a user retweeted another user, we don't have a direct relationship between those users saying this user retweeted this user. We could create that relationship if we wanted to, but it's kind of redundant because the data already exists within this model where the user posted a tweet, that tweet retweets this tweet, and this other user posted that tweet. So, I mean, we could create that direct relationship if we wanted, but it's easy enough to go ahead and infer that direct relationship from a Cypher query, and then within R, we can then take that further, this subgraph further. So in this subgraph, it only consists of users, and two users are connected, again, if one user retweeted another. So stat545 apparently retweeted Millard L one time. That's what this edge list means. And again, we use the Cypher function to grab that data out of Neo4j. Then to convert this edge list that we grabbed out of Neo4j to an iGraph object, it's as simple as saying, is using the graph from data frame function within iGraph, which expects an edge list that we just created. So an edge list of from node to node, and then optionally a weight. And then so we're just passing that edges data frame to a graph from data frame, which is an iGraph function. And then IG at this point is an iGraph object. Then once you have your subgraph, as I'm calling it, loaded into iGraph, at that point you have all the graph algorithms ever, pretty much, under the sun at your disposal. So for example, I can find out who has the highest betweenness centrality in this subgraph of users retweeting other users. And that's done very easily with just the Betweenness function, which is an iGraph function, which expects an iGraph object. And betweenness centrality, if you've heard of it before, is a fairly popular centrality measurement on graphs. It essentially counts it finds all the shortest paths between all pairs of nodes in the graph, and then for each node, it counts how many times it's been on a shortest path, and then that's its betweenness centrality. And then sometimes they'll also divide by the total number to scale it, but I think iGraph, it actually just counts how many times. So we we were able to easily get this information by passing that iGraph object to the Betweenness function, and then sort it decreasing, and we see that Hadley Wickham has the most number of, or the highest betweenness centrality, and that's usually a measure of, as the name suggests, the centrality of a node. You know, how many times is it on a shortest path? Because that usually indicates that that user, or that node, is very central to the graph. So we were easily able to get that information with just a couple of lines. All right, and of course, just to show how versatile this is, you can just grab any graph algorithm and pass the iGraph object to it and get the answer. So here we're finding who has the highest closeness centrality in this subgraph. And the closeness is the reciprocal of the sum of the distance of this node from every other node in the graph. So the distance of a node is, from every other node is, for each node, it finds the shortest path to all the other nodes and then sums all those distances. And then the closeness is just the reciprocal of that sum. So just a different centrality measure, a slightly different centrality measure as we see here. So the same thing applies where we pass the iGraph object to the closeness function to get that information. We're going to sort it descending. And we can see that it definitely is a different centrality measure because the same names aren't in the top here. We have different users. So we have ecology and the data science LA blog at the top there. So a different centrality measure, but I'm going to hold questions till the end if that's okay. But it's fun that you can easily and very quickly play around with these different measures within a handful of lines of code. All right, let's look at some graph visualization. So there's lots of ways to visualize graphs within R. One of those ways is just built into iGraph itself, which is quite nice. There's lots of different customizations you can make to the graph. You can label it with text and whatnot. Here I've removed the labels just so it wouldn't be too busy to look at. But lots of customization available, and then it's as easy as passing that iGraph object to the plot method, or the plot function, rather. And then this is the graph that we created earlier when we grabbed that subgraph of users retweeting other users. So again, each node in this graph is a user, and then two users are connected if a user has retweeted another user. So that was as simple as passing the iGraph object, which is IG again, to the plot method. And then we got this graph. Additionally, we can also color our graph. There's many ways you can do this. Here I decided to run a community detection algorithm, which again, all of the ones you could ever think of are most likely built into iGraph already, so you don't really have to do any work at all, which is quite nice. So here, I'm running the edge betweenness clustering algorithm, which is it's the Girvan-Newman algorithm. It's a fun read if you're into that kind of thing, reading academic papers. Essentially, it iteratively removes edges with high betweenness until there's a disconnected graph, and then that determines your communities. But long story short, all you have to do is pass your iGraph object to cluster edge betweenness, which is just another iGraph function. And then that clusters variable is the cluster assignments, along with some other metrics on the clustering algorithm that it just ran. But we can easily assign the color of the node to its membership among the clusters that the algorithm determined. And then we can replot the graph now with the colored communities. So this is a fun exercise if you want to determine if there's any clear community building among your graph. So if I had maybe some labels on this graph, which we're going to see in a few slides, we could see communities of people, tweeting about relatively the same topics or tweeting among each other. Because remember, this is a retweet subgraph. So we can see there's communities of people who retweet each other quite frequently, but then don't really interact with other users on other sides of the graph. So again, in just a couple of lines, I was able to run a community detection algorithm and then color my nodes by the community assignments or the cluster assignments, and then visualize that result. OK, we're going to look at a more fun version of graph visualization. So the iGraph visualization is static. It just gives you a PNG of your graph. But it's way more fun when you can click and drag your nodes around and zoom in and out. So we're going to go into a library I discovered not too long ago, actually, called VizNetwork. And it uses viz.js to visualize your graph. And so that's installed with install packages VizNetwork and then loaded like so. And then it expects both a nodes data frame and an edges data frame to create your visualization. So we're going to have to do a bit of data manipulation here. But we're just taking our initial edges data frame where we had the edge list of user retweeting other user. And then getting the unique names out of that, because it expects a nodes data frame that just has the unique node IDs and whatever label you want on that node. So we're just creating that real quick, and that's what that looks like. It needs a unique ID, which happens to be the same as the label in this case. So a couple of lines to get that set up. And then it's as simple as passing the nodes and edges data frames that we've created earlier from our Cypher queries and from our manipulations to create a graph that is now interactive, and I can move it around and it bounces around, which is super fun, of course. So now you can actually put labels on your nodes. You could have done labels in iGraph, but because it's a static image, if a label's on top of another label, it's not going to move out of the way, and it's just pretty hard to read and to work with. Whereas when you put your data into a JavaScript library, it's much easier to manipulate, and it's much better as a forward-facing, a user-facing feature. If you were to perhaps build an application on top of your data set, you'd want to use something like this over an iGraph visualization. So this is a pretty fun library. You can also see the users' names at this point, and I'm pretty familiar with the RStats community, so I can see, oh yeah, these guys, they all work on the open science platform, and these guys, they all work on what have you. So it's pretty fun to see these communities that obviously exist within the RStats community. And here's the Hadley-Wickham node that had a very high betweenness centrality. And I also wanted to show that you can very easily customize VizNetwork to also display the results of your community detection algorithm. So remember I had that clusters variable that had the membership assignment from the clustering algorithm in there. So all I had to do was add a group column to that nodes data frame. So here I'm saying the group column is equal to those cluster memberships for all the nodes that we determined earlier. And then just replotting. So reevaluating that information and passing the nodes and edges data frame to the VizNetwork function. And then this is the same graph that we just looked at earlier, except now we have colors indicating communities. So here's people talking about the R bloggers blog, and then here's trying to look for here's the open science people right here in blue. There's the open science Twitter, and then here's the main guy who runs it. So it's fun to see all the same people who are working together on a project in the same community after you've run a community detection algorithm. So that is VizNetwork, and probably my preferred and recommended way to visualize graphs within R. OK, and something I wanted to do for fun, to wrap it up, is association rules. You've probably actually heard of these, and you might not know it. They're used by like retailers. Actually, let me skip. So these are the two packages I'm going to be using the A rules package will allow me to do the association rules, and then tidier is for doing some manipulations with the data. So retailers and grocery stores will use these a lot, especially online retailers. They'll say, OK, you have these two things in your cart. What's the conditional probability that you also add this other thing to your cart? And they'll use these to recommend things in your sidebar. And so this is used both online and offline. So like online retailers, they have algorithms running in the background that fill up your sidebar as you're clicking, like Amazon. When I don't know what they do exactly, but hypothetically, you add two things to your cart, and then it says, OK, you have these two things in your cart now. Now we know the conditional probability that you also add this other thing. Let's order these recommendations in your sidebar by these probabilities. So a classic one is if you have onions and potatoes in your cart, then you're going to probably buy burgers. So offline retailers also use this in the way that they put things, or how they organize their grocery stores. They'll put things that you frequently buy together in the order that you usually buy them. So this is a classic association rule, is that if you have onions and potatoes in your cart, then you'll probably also buy hamburger. So grocery carts are fun and all, but I wanted to do this with hashtags just to see if we found something interesting. Given that it's not really the same idea because you pick all of your hashtags up front, but I wanted to see, given that you have this hashtag in your tweet, what's the probability you also have this other hashtag in your tweet with conditional probabilities? And these association rules are mostly, there's lots of different metrics you can use to figure out which of your association rules are important and which are not. I decided to use lift, which is just a measure of, it's a ratio of the joint probability divided by the probability if they were independent events. So we're going to use this metric. So you could do this with Cypher if you wanted. I wanted to show it was possible. So let's say we were interested in the association rule between the hashtag rstats and then the hashtag analytics. So given that you have the hashtag rstats in your tweet, what's the conditional probability that you also have the hashtag analytics? So if I wanted, I could calculate the lift with a Cypher query, but this doesn't scale. The whole point of association rule mining is that you don't know what rules are important or interesting up front. So here, I picked a rule out of my head at random and then found the lift. And a lift less than 1 is not good. So this rule isn't very interesting or exciting. But the point of these association rule algorithms is that you don't know ahead of time what is interesting, so you want to let the algorithm figure out for you. So this doesn't really scale, and it's not very interesting when I have to pick the rule myself. But what we can do is grab all of the hashtag tagging tweets data out of our data set. So a pretty simple query here to get the hashtags, the tweets, and we're returning the ID of the tweet and the name of the hashtag. Again, just using that Cypher function. And so now our data is in long format at that point. And then we can pretty easily convert it into wide format. Here we just have a data frame where each row is a tweet, and then each column is a hashtag, and then we have a matrix saying true and false. This isn't a very good example because they're all false. But like if tweet number 1 had the Amazon hashtag in it, then that value would be true. So this is just a matrix of true, false Boolean saying this tweet did have this hashtag. So this is the format that the A rules package expects your data to be in before you run this algorithm. So we've converted it to a transactions style. That's what the data object that it expects. So we have 424 tweets. So not a ton of tweets. And then we have 83 items or hashtags in this example data set. And then it's as simple as passing it to the a priori algorithm, which is the classic algorithm for determining association rules. So we've just passed that data frame or that data object in. We've set a few parameters, and then it shows you all this output of what it's doing as it figures out your association rules. And then you can figure out the rules. And here I'm sorting them by that lift metric that I showed earlier. It's the ratio of the joint probability to the independent probability. And I'm just showing the first one here. So here, this was determined to be the most interesting, or to have the highest lift association rule. It's showing you the left-hand side and the right-hand side of the rule. So it's saying that if you have hashtag big data in your tweet, at least in this very small sample of tweets, then there's a high conditional probability that you'll also have the hashtag rstats in your tweet. So that was just a fun exercise, and just to show how pretty easy it is to take a package like A-rules and combine it with your Neo4j database to infer some interesting association rules out of your data. So, conclusion. So this is the workflow that I showed today, and this is the workflow that I also use professionally day in and day out, because I work with Neo4j and R professionally. So I use Neo4j to store all of my data. Of course, it's a fully transactional ACID database, so it's sitting there in the back end all the time collecting data. And then I'll often connect with R Neo4j to write queries and pull my data into R. And then once, of course, I have my data in R, I'm free to make visualizations or run algorithms that I just showed. So that is my day-to-day workflow, and the workflow that most people would use if they were to combine both Neo4j and R. Any questions? That's my Twitter. I'm most responsive on Twitter. Don't email me. I'm awful with email. And then that is my GitHub for the R package, if you want to check that out. Thank you, everybody. Yeah.
You touched upon it, for example, the Betweenness computation. You showed that you could do it in a cipher, but you'd rather do it in R. So where do you draw the line, like what computations do you do in cipher, and when do you choose to do it in R?
So the question is, which computations do you prefer to do in Cypher, and which do you prefer to do in R? All of those I prefer to do in R. I tried to make it clear at the beginning that Neo4j is a database. It's not a graph compute engine. It's not meant for global graph queries. Betweenness centrality is a super expensive algorithm. You have to find you have to find the shortest path between all pairs of nodes. That's not a very database question. That's a compute engine question. So so betweenness centrality, absolutely. You could do that in Cypher if you wanted. I have done it in Cypher on very small graphs. You wouldn't want to do it on a production database, that's for sure. That's something, if I were going to do it in Cypher, I'd pull a backup of the database and do it on a backup offline. So you could do it in Cypher. And then I think the association rule, the lift, I think I also did that in Cypher just to show that you could. And that's actually a very quick query. There's nothing wrong with doing that. It was for a different reason. It was for the reason that I had to think of the rule ahead of time. I had to think of the association rule, whereas the whole point of association rule mining is that you don't know ahead of time what the rule is. You wanted the algorithm to find it for you. So yeah, for the most part, if it's a global graph query, I don't do it on Neo4j. Or I'll do it in R.
But one of the major concerns is that people don't want to load the Neo4j running instance. We want to offer computation on some other node, and that's why
Absolutely. Yeah, so yeah, same question. Well, a lot of people, like in production, they have a clustered environment with masters and then replicated slaves. And then what I do is I just pull a backup and do everything offline if I want to do a big global operation like that. Some people will just do it on a particular slave. And then, because they actually want to write back, they'll want to do, I can do this in R as well, where I figure out the betweenness centrality and then I write it back to the graph as maybe a property on a node. But some people like to do that just within. They'll write a Cypher query to do this kind of thing, and then write it back within the same transaction, and then they want that to be replicated across all the slaves. So, but yeah, there's several ways to do it. Yeah. So the question is, he uses Python for data analysis. Is it as easy as doing it in R? And absolutely it is. I have several Jupyter notebooks on doing the very similar things within Python. Find me after, and I'll show them to you, actually. You can find them on my GitHub if you click around. There's like 3 Jupyter notebooks. I recommend the Py2Neo module. But there's several modules that work really well with Neo4j. We should meet up after, and I'll show them all to you. All right, thanks, everybody.